So let's wrap up the summer semester with Chapter 9, and we're only going to do select sections from this. So Chapter 9 is very loaded, and we only want to cover a few things. First of all, we'll talk about states of matter. There are 4 normal states of matter that we're used to studying. These 4 states would be the things you learn in elementary school. We have solids, we have liquids, and we have gases. These are the big 3, and then finally we also have plasmas. If we take all of the atoms that go into solids, liquids, gases, and plasmas, add them up and figure out how much of the universe they comprise, they actually only comprise 4% of the known universe. 24% of what's out there we believe to be something called dark matter. We don't really understand what it is. That's why we call it dark. So 24% plus 4%, that gives us 28%, which leaves another 72% of the universe that we don't know what it is, and currently we think that that is this thing called dark energy. So these are our various states of matter. We have the 4% that we understand pretty well, solids, liquid, gases, and plasmas. We have 24%, we call it dark matter. Dark because we don't know what it is, matter because it is some type of matter, we think. And then 72% is dark energy. So we've talked about states of matter. Another key concept that we're going to discuss in Chapter 9 is the concept of density. This revolves kind of around the question that you might have been asked before: what weighs more, a pound of feathers or a pound of lead? And scientists ask people this question, random people on the street. 8 out of 10 people answer a pound of lead. Of course, this is the wrong answer. A pound of feathers weighs exactly the same as a pound of lead. They're equal to each other, yet 80% say a pound of lead is heavier. This is because intuitively in their mind, they're thinking of the concept of density. We describe density with the Greek letter rho, this curly p, and it's equal to an object's mass divided by its volume. So to get a pound of feathers, you need to stack a whole lot of feathers together to equal a pound. So it seems like it's a larger quantity than a pound of lead, even though they both weigh the same. If we think a little bit further on density, like all quantities in physics, density has units. The units of density are going to be the units of mass divided by the units of volume, and that is going to give us that the units of density are kilograms over meters cubed. Volume is a length times a width times a height, so it's cubic length. So we've talked about states of matter, we've talked about density. Another big key concept, and this is going to be probably the biggest one we study for Chapter 9, is the concept of pressure. Now, to talk about pressure, there's a couple different ways we can do it. And since I seem to be a fan of buckets of water lately, let's take a bucket of water. Of course, it's water, so it should be blue. And we're going to take an ice cube and stick it inside of this bucket of water. Here's my ice cube inside of my cup of water. Now this ice cube is floating here, and it's being pushed on in all directions by water. So there's some water that's above it that's kind of pushing down. There's some water to the sides that are pushing side to side so the ice isn't moving left or right. And we have some water that's pushing up from the bottom. And we're going to say, let's say this piece of ice is a certain depth below the water. We'll say the bottom of it is a distance y1 from the top of our water, and the top of the ice cube is a distance y2. So we're just describing this ice cube. We have the bottom is a distance y1, and we have the top, which is a distance y2. So describing where this ice cube is inside of this cup of water. We know the water is supporting the ice. The water is supporting that ice by supplying a force, by supplying a normal force that kind of buoys up, keeps this ice floating. This water force that's being applied is being applied over the entire surface of the ice cube. The way we can describe that surface, so that's going to be a cube, it's going to be a square, and it's going to be some area that the water is pushing on to hold up our ice cube. And this push, this force that the water applies over this given area has a specific name. It's pressure. So the physics concept of pressure is equal to a force that's being exerted over an area. So I'm applying a force. In this case, my water is applying a force up. The water is also supplying a force pushing down over the area of this ice cube, the size of how big this ice cube is. So the units of pressure, we can figure out what these are. Units of pressure are going to be equal to the units of force divided by the units of area. The units of force, of course, are the newtons, and the units of area are square meters. So there we have our units of pressure. So this is going to be a useful equation. No, pressure is force over area. Units are newtons per meter squared. So we're going to return to our little ice cube example. Let me draw my cup. Let me draw my water. Let me draw my cube. And I'm going to do a force diagram. Identify all the forces that are acting on this piece of ice. A free body diagram. So, as usual, here's our little ice cube, and we know we have the force of gravity that's acting to pull this ice cube down. Of course, it's not going down because it's buoyed up. It's being supported by another force that's being applied up. A force being applied up. That force is supplied by all this water that's underneath our ice cube. So all this water down here is buoying up our ice cube, applying an upward force. But then we also have some amount of water that's kind of pushing down on this ice cube. The water that's weighing it down. So we have all the water that's above it that's going to weigh it down and also apply a downward force. So this water is going to be pushing down on our ice cube, and we'll call this F down. And we can write out the sum of forces that we have acting on our little ice cube. First, we have one force acting up. That is going to be F up. That's one F'd up force. And then we're going to have two forces acting down. The force of the water above the ice cube pushing down, kind of weighing our ice cube down, minus the force of gravity. And since our little ice cube is just floating inside of our cup, the total mass times acceleration is going to be 0 because our little ice cube isn't moving. Now if we go back to our definition of pressure, pressure is equal to force per unit area. So we can solve this equation for force. Force is equal to pressure times area. So we can use this. Actually, we can use this force equation right here and plug in for pressures. Instead of using forces, we're going to solve this Newton's second law equation in terms of pressures. So we have some pressure that's pushing up. We will call that pressure 2 pushing up times the area of the ice cube. And we're going to have some force down. The force down is going to be the pressure down. I can call that pressure 1 times area. Pressure 1 is going to be the pressure of all this red water weighing us down. Times the area that it's applied over, the area of this ice cube. And then finally we'll have the mass of our cube times g, the force of gravity acting on it, on our cube, is equal to 0. Let's take a closer look at m. Take a closer look at the mass. We remember density is equal to mass divided by volume. So we can solve this for mass, and if you find that mass is equal to density times volume. So we're just kind of doing Newton's second law problem, except we're doing it in terms of new variables, new quantities, things that we're learning about in Chapter 9. So we can replace our mass with our density equation. So let's do that. This will give us pressure 2 times area, the amount of force that's holding us up, minus pressure 1 times area, the water pressure that's pushing down on our ice cube, minus m times g is equal to 0. So we're repeating our equation from before. We substitute in for our mass, pressure 2 times A minus pressure 1 times A minus density times volume, which is just equal to mass, times G. It's going to be equal to 0. Now the volume of our ice cube is equal to the length times the width times the height. The length times the width is just the area of our ice cube. And if we quickly sketch out this ice cube again, here's our little cube of water, and we said there was a height y2, or y1 was how far the bottom of the ice cube was, and y1 was the distance to the, y2 was the distance to the top. So the total height of this ice cube, cube height, has to be equal to y1 minus y2. So we do the length times the width times the height. Length times width is area. Height is y2, or y1 minus y2 to get our volume. And we plug in our volume. So we find P2, the pressure underneath our ice cube, times the area, minus pressure 1, the amount of water pushing down on the cube times the area, minus density times area times y1 minus y2 times g is equal to 0. What we can see here, there's area in every single one of these equations, so the area kind of cancels itself out. And we can solve this for pressure 2. It's going to be equal to pressure 1 plus density times y1 minus y2 times g. And if we think about what y2 minus y1 was, it was just the height. It was how far below our surface we were. To our final equation for pressure. Pressure at some depth, some distance below the surface, P2, is equal to pressure above P1 plus density of whatever liquid you're floating in times g, the acceleration due to gravity, times h, how far below the surface of whatever you're floating in you are. This gives us our general equation for pressure at a depth. At a depth that's equal to h. We have more things that we can do with pressure other than figuring out pressure on a piece of ice floating in a cup of water. We have something called Pascal's principle that has to do with pressure. Pascal's principle. Pascal's principle says that a change in pressure in an enclosed fluid is transmitted to every point in the fluid. So that's a change in pressure on an enclosed fluid goes to every point in that fluid. What the heck does this mean, and how is it actually useful? Well, it's used in something called hydraulics. Hydraulic presses, hydraulic lifts. Hydraulics depend on pressure. Something that's used in a lot of auto garages. So, how does a hydraulic press work? Here we have a nice little picture of what actually occurs with a hydraulic press. We have Dr. Bubar. We know it's Dr. Bubar because he's got short little legs, and Dr. Bubar's got short little legs that should be a lot longer than they actually are. Dr. Bubar. And he's standing on one side of this little hydraulic press, standing on this little plate. Now on the other side, we have Rachel's car. Rachel is Dr. Bubar's wife. So Rachel's car needs to get fixed. Dr. Bubar's cheap, thinks he can fix it himself because he's a physicist and is a conceited jerk. So he thinks he can fix this car if he can just get it lifted up and look underneath it. And he's going to use the hydraulic press to do that. So the car is sitting on this other plate, this other size plate, and Dr. Bubar just needs to raise it up. Now inside of this hydraulic press, there's fluid throughout this whole thing. So we have an enclosed fluid, an enclosed incompressible fluid. So we can't compress this fluid at all. It's not gonna move. It's enclosed. So we're gonna demonstrate Pascal's principle right here. Pascal's principle says that if I apply a pressure on one side, then that pressure is exerted to every single point. Every single little bit of this water is going to feel that same pressure. So if I apply a pressure, if I apply a force over a unit area on this side of the plate, I should get out that exact same pressure on the opposite side of my plate, because that pressure that I apply over here will be transferred throughout every single part of this fluid all the way over to my larger plate. So the pressure on my first plate has to be transferred through the fluid and into the pressure on my second plate. Now the really nice thing about this is pressure is force divided by area. So pressure 1 is force 1 divided by area 1. And that's got to be equal to force 2 divided by area 2. In this example that we have, force 1 is going to be the force that Dr. Bubar exerts by standing on a plate. So that's going to be Dr. Bubar's weight divided by the area of this plate. So it's got a very small area. So this can give us a big difference in force in this fraction. If the force of Bubar is much bigger than the area, if the force of Bubar is much bigger than the area, then we end up with a big number over here, and that means that we'll end up with a big F2 that we can lift up on the other side of this hydraulic press divided by whatever area we have of our second plate. So let's do a numerical example. Let's figure out what kind of force we can lift up. So with a hydraulic press, we've already established that pressure 1 on one side of the press is equal to pressure 2. So force 1 divided by area 1, pressure is just force divided by area, is equal to force 2 over area 2. I want to know how big of a thing I can lift with my hydraulic press, so that's going to depend. So that's going to be what F2 is. So I solve for F2, multiply both sides of this equation by A2, doing a little bit of simple algebra, and I get F1 divided by area 1, the force that I apply divided by the area that I'm applying it over, times the area of my second plate is equal to the force of what I can lift. Typical numbers for a hydraulic press. So a typical force of a person, the force that a person will usually exert, it's going to be something like 75 kilograms. So that's going to be the person's mass, that's about my mass, times, we'll say acceleration due to gravity is around 10 meters per second squared, to make the numbers a little easier. So force 1, the force being exerted, is going to be 750 newtons. Typical area of a hydraulic press, area 1, the small area, probably around 0.3 square meters is a reasonable number. Area 2, the area that we put our that we want to put a car on, we probably need about at least 25 square meters to lift up a car. So that's the pressure that we need. That's the area that we need on a second plate. A car needs about 25 square meters of space. So let's plug in all of our numbers and find out how big of a force we can lift. How much weight can Dr. Bubar lift up? Can he fix Rachel's car? So we'll plug in all of our numbers. Force 1 is 750 newtons. Again, force 1, 750, divided by area 1. Area 1 is 0.3. We'll tack our units on here, make sure that our units are coming out as we want them to, times, we're multiplying by area 2. Area 2 is 25 square meters. And if we multiply all this out, force 2, the force that I can lift with the hydraulic press, we see our square meters cancel. We're going to end up with newtons. That's a good thing. And the final answer that we find is 62,500 newtons. I could back out the mass that I can actually lift. So this is a force. F2 is equal to the mass that I can lift, mass 2 times g. So the mass that I can actually lift, I need to divide this by g to find mass 2 is equal to 6,250 kilograms. And since we're Americans and refuse to use kilograms, this is America after all, we are going to find the total mass we can lift is 13,780 pounds. Is this enough to lift Dr. Bubar's car? To know this, we need to figure a big truck. Big Bubba truck. Dr. Bubar doesn't ride a big Bubba truck. So this is the best case scenario. How much mass is a big truck? Something like a Ford F-150. Big truck weighs 2 tons. 2 tons is 4,000 pounds. Dr. Bubar's car, Rachel's car, is a tiny little Mazda hatchback. About the cheapest little Mazda hatchback you can buy. So can he lift it? I think so. He can lift about 3, or maybe 4, maybe 4 cars. All with the hydraulic press, which works by Pascal's principle, where the pressure on one side is applied to every single part of the fluid. Your book, I think, gets a little confusing at points. At one point, we've been introduced to this equation already. Pressure at some place, at some distance, at some depth in a fluid is equal to the pressure at the surface plus the density of the fluid times G times the height, how far down inside of that fluid you are. At some point, your book does this. It says P is something called an absolute pressure. So that is the pressure that you actually would measure. And then they take this equation, they take P minus P naught, P0, the initial pressure, is equal to rho GH. And they say this is something called a gauge pressure. And a gauge pressure is a pressure that's relative to atmospheric pressure, the pressure inside of the atmosphere. So there's one good example that I can think of to demonstrate gauge pressure, and that is a car tire. So if you look at a car tire, here's my car tire, I've got some treads, some jiggly treads, maybe I've got some nice rims, no, I want chrome rims. I've got some nice chrome rims on my tire. They spin when I'm cruising around listening to P.D. Pablo. So this tire is being assaulted on all sides. It's being attacked on all sides by the atmosphere. The air around it is actually pushing in on the tire at all places. Atmospheric pressure constantly pushing in, much like the ice cube in the glass of water. In that case, it's water pushing in. In the case of the tire, it's the pressure, the literal pressure of Earth's atmosphere pushing against the tire. Now, when you read your tire pressure, the pressure of your tire is actually equal to some gauge pressure plus some atmospheric pressure. So again, we have this gauge pressure. So you read the pressure in your tire, and the pressure in your tire, when you read the pressure in your tire, you have the little pressure nozzle thingy that you stick in, and it reads some certain pressure for you and tells you how much air you have in your tire. Maybe something like 32 psi, 32 pounds per square inch. That pressure is the pressure you read from a gauge. the pressure inside of your tire is actually equal to that pressure plus the pressure of the atmosphere. The tire has to be able to push out at least atmospheric pressure. If it wasn't pushing out with an atmospheric pressure, then all these pressure of the atmospheres was squeezing into the tire, squeezing the tire down, would cause it to deflate. So you have to realize that the gauge pressures that you're reading, this 32 psi that you usually put into your tire, is 32 psi plus the pressure of the surrounding atmosphere to give you the pressure inside of your actual tire. This doesn't work in just a tire. It actually works inside of our bodies too. If you've heard of blood pressure. So your blood's moving around in your body. If you take your blood pressure, that's going to give you the gauge pressure. But the purpose of all of that blood flying around is to provide this gauge pressure and to provide enough pressure to resist the atmosphere. So we're in essence constantly fighting with our own atmosphere. Our blood moves to counteract the atmospheric pressure. So we can carry this concept of pressure a little bit further to the concept of Archimedes' principle, also known as buoyant forces. The word eureka is rumored to have come from Archimedes' discovery of this buoyant force. So the buoyant force, or Archimedes' principle, says that any object submerged in a fluid, so if you put something inside of water, anything in a fluid, is buoyed up put that in parenthesis, in a quotation mark, is buoyed up by a force with a mass equal to the amount of fluid it displaces. So what the heck does that mean? If you've ever taken a bath, so here's our bathtub. We have some nice claw bathtub legs. And we have some water level. Here's my water level. And then something's going to happen. So let's make this original water level a dotted line water level. Dotted line, that's the original height of the water. Now, once you step into this water, once a person is sitting inside of this water, what happens to our water level? The water level is going to go up. And apparently our little person is going to drown. Now the amount that this water level went up, and we can figure out what that is the displaced fluid. It's the amount of water that actually rises when you get into a bathtub or something. This is the displaced fluid. And if you weighed that displaced fluid, it would be equal to your weight. So this gives us the concept of the buoyant force, where the buoyant force is equal to the mass of the fluid displaced times the gravitational force. After all, Boolean force is a force. Now, using the stuff that we've been learning for Chapter 9, mass we can rewrite in a slightly different way. We can rewrite it as density of whatever fluid we're inside of times the volume of the fluid we displaced, volume of our fluid, times the acceleration due to gravity. And this is going to be the general equation for the Boolean force and for saying Archimedes' principle, where the amount of fluid displaced is equal to the weight of the object that does the displacing. Okay, we're in the home stretch. We're going to talk about something called fluid flow and something called Bernoulli's principle, and then we'll be done with Chapter 9. So in fluid flow, let's ask a question. Let's say I send some water into this pipe. I send some water in, and that water is going to go flowing through this. I send it in at some speed, initial speed v1. And then it goes through this pipe, very tight pipe at the beginning, so it's going very, very fast. And then the pipe kind of expands outwards. The pipe gets bigger. So what's going to happen to this water as it's going through to this large part of the pipe? The water is going to slow down. It's going to be able to spread out. It's going to have more room. So we know intuitively, hopefully, and we can clearly see that this velocity at the second end of the pipe is going to be less than the velocity at the first end. That the water is going to have more room to go through. It's going to have more options, so it's going to spread out and go a little bit slower. This is the concept of fluid flow, and we could do a lot of derivations. We could compare the area at the beginning of the pipe times the velocity at the beginning of the pipe and see that it's going to be equal to the area at the end of the pipe times the velocity at the end of the pipe. This is an equation called the continuity equation. We can derive all these things, but since we're on a truncated time scale, we'll just take you straight to the final result. The most common explanation of the continuity equation, which really does just come from this concept that the area times the velocity at the beginning ends up being equal to the area times the velocity at the end. Notice we have a big velocity and a little area, and we end up with a big area and a little velocity at the end. So we're keeping things constant. We're keeping things continuous throughout the whole pipe. And if we do this and use pressures and densities, we find pressure 1 plus 1/2 density of our fluid times velocity of our fluid 1 squared plus rho times g times y1, however tall this first part of the pipe is going to be equal to pressure 2 plus 1/2 density times velocity of the that you're leaving the pipe with squared plus rho times g times however tall this second part of the pipe is. We're invoking a few extra things. We're invoking kinetic energy. There's a kinetic energy term here, and potential energy term here, kinetic energy here, potential energy here, and using some kind of conservation of energy and work to get to this equation. But we can get there. If you want to see the details, you can check out my lecture notes. They are in there. But this is the most general statement of the continuity equation. And the important thing to note about this continuity equation, the important concept that we get from this whole derivation, is that the sum of pressure kinetic energy per volume this is going to be that 1/2 rho times velocity squared, and potential energy per volume has the same value at all points in a fluid. In a fluid stream. So this is really just kind of like Pascal's principle extended to flowing water, to water in a river, or water in a pipe, or situations like that. You might see these in your homework a little bit. Now the final point that we need to know for Chapter 9 is this guy named Bernoulli. Sounds kind of like a microwave Italian dish, but no, not nearly so delicious. So Bernoulli has this principle. Bernoulli's principle says the following. An increase in the speed of a fluid yields a decrease in pressure. So this is Bernoulli's principle. Faster speeds equals low pressure. And correspondingly, that means that slow speeds equals high pressure. The best example of this is in aerodynamics, aeronautics, in the lift of an airplane. So let's draw ourselves a nice little picture of an airplane wing. So here's our airplane wing. Our plane is moving along, it's moving along in this direction, and there's going to be air flying along this plane. Now, as we're moving along, the air comes along, and it kind of smacks into this wing. On the bottom, it smacks in and kind of gets slowly dragged along, and the air is moving a bit slower underneath the wing. So we have slow air moving down here. So what does that mean for the pressure according to Bernoulli? According to Bernoulli, slow air equals high pressure. So we have high pressure underneath this wing. High pressure pushing our wing up. High pressure pushing us up. Now what would be really fantastic is if we had low pressure above the wing. If we have low pressure above the wing, that means what? If we have low pressure up here, then the high pressure pushing up into a low pressure area means that the plane can lift off. The plane can move up. So the purpose of the wing is to kind of compress the air, to make it get bundled up right above and just above the wing. So we bunch up a whole bunch of air, and that air is moving really fast. Fast air gets kind of bundled up as the airplane wing cuts through the air. So the air getting cut through really quickly leads to fast air above the wing, which means we have our desired low pressure. So a high pressure pushing the wing into a lower pressure area means that our airplane can lift up and our airplane will fly. So Bernoulli's principle governs airplane lift. It's the best example that I can think of for Bernoulli's principle. And that is the end of chapter 9.